Okay. I think more people were coming later. Okay, so before we get started, one announcement. So the first anonymous evaluation is open. If 90% of you submit an evaluation, then everyone gets 10 bonus points. The same thing for the final evaluation. There are 2 evaluations in the class. So last class, we talked about buffer overflow, and you took a look at different share code, and we learned how to put share code in different places in the address space. As long as we can get them in the address space, we can jump to it. We can get the share code running and eventually get a share or steal the secret. So in this class, we were learn a new technique. Instead of overwriting the return address, in this case, we don't have the luxury to overwrite the return address. We can only overwrite the saved EBP or saved RBP on stack. This is a part we have chosen to ignore so far. We just put garbage there, but actually that is also a place we can utilize to attack the program. After that, we talk about the defenses available in current CPUs and OS for defeating buffer overflow. We will talk about several approaches today. Then 2 weeks later, we will talk about more approaches. Next week, we're going to have our very first fall break. So no homework due next week. It will be due before the class 2 weeks later. So here we have the share slide, share code, and also long share code. We are going to use them today. Okay, so how many of you solved the Crack Me for the hard version? You solved that? Good. You 2? Okay, great. So better than last year. Last year, only 1 guy solved that. So this year, 2. Okay. So did you jump to the beginning of a print secret or? Okay, cool. Then we will go over this briefly. So this is the source code for Crack Me 4. Both the regular version and the hard version, they have the same source code. The only difference is when we compile them, we give different flags. So there is a main function, there is a buffer, 8 bytes, source code level, and it looks for command line arguments. It doesn't look for stdin input. It copies your input to the buffer. Use a string copy. That's why there is a buffer overflow here. So your job is to return to the beginning of print secret, which means you have to set up 3 parameters here, I, J, K. And they are hard-coded values. So if you do an obj dump or disassemble this program, use any tool, you will find those hard-coded values. If those parameters match, the program will call print flag, give you the flag. Otherwise, it will just exit and do not say it has any error. That's why you will not say a segment fault, or it basically do not give you any information here. So this is the disassembly of the Crack Me 4, the regular version. So to hack this version, you need to put the address of the function print secret at the return address, then 4 bytes of garbage, then just put 3 arguments here. So 2 weeks ago, I explained why we needed this 4 bytes of garbage. I say many people missed this part. If you do not understand why we need that 4 bytes, go back to the video to try to understand this. So for the harder version, you can see the main function is a little bit longer, several more instructions, and the instructions in the red boxes, those are the new instructions that didn't exist in the regular version. So let's take a look at those instructions and try to understand how we crack this one. Assume we are at the beginning of this function, this main function. This is a main function, so it is called by the C library function, libc main, something start main. So at the beginning of this function, the stack pointer ESP where points to a return address on the stack. And that return address is actually somewhere in the middle of that libc start main function. So when main function returns, if there's no attack, we are supposed to return to that function. So 4 bytes higher, we have the first argument of main function. The main function takes 3 arguments, and the first one is argc. How many arguments are there? Command line arguments are there. Then after that, we have several pointers, argv0, argv1, those kind of stuff. So the first instruction, NBR32, we ignore that. The second instruction, we're actually getting ESP plus 4 to the register ECX. So after the first instruction, ESP still points to the return address. ECX will point to return address plus 4, right, which is actually the argc address. So that is what this instruction is for. So after that, we have a logic AND instruction. We add ESP with this hard-coded number, 7 Fs and a 0. So the purpose of this is, so when you add any number, a logic AND any number with this number, 7F and 0, then the least significant 4 bits will be changed to 0, right? So the purpose of this instruction is actually do some kind of alignment. We are trying to align the ESP to 16 bytes. We don't know how many bytes we are actually moving ESP down. That depends on runtime, what it really is the address of ESP. But we know that it will be smaller than 15 bytes. At most, it's 15 bytes. So after that, ESP will move from here to here. And the size between those 2 addresses will be at most 15 bytes. The actual bytes, you may need to debug to figure out. Only looking at the code, you don't know that, right? Static time, you don't know. Only runtime, you can know the size. So after that, we have a push, what ESP minus 4 points to the stack. ESP points to here. So ESP minus 4 actually points to the return address. We push this to the stack again, so we have another copy of return on the stack. Okay. So the whole purpose of this, what the compiler trying to do is trying to align the beginning of the stack of the main function to 16 bytes. Somehow, compiler believes that will make the system program run faster. That's why the compiler is doing that. Then after that, we just have our regular prologue of function. We push EBP, move ESP to EBP. Then after this, both EBP, ESP points to this place, and the ECX still points to here. Then we have another push the ECX. So the ECX value will be pushed onto stack. ESP will points to the saved ECX, and ECX points to the argc. The saved ECX, this will be a pointer. This will be pointed to here. And ECX, we haven't changed that yet. Then, in the middle, we just make the regular calls. This is the same as the previous regular version. If we look at this one, here we have this string copy. Now, if we look at the string copy, this is a string copy, and the parameter is in EAX. The first parameter. The string copy takes 2 parameters. The first one is a destination. The second one is a source. The first parameters was pushed to the stack last. So that's why this push EAX is pushing the destination, and the destination is at EBP minus 10. Okay? So now we know that EBP points to here, and the EBP minus 10 points to this place, which means 10 in hex, which means EBP and the EBP minus 10, in between there are 16 bytes. And we already know that the saved ECX used 4 bytes, which means the buffer in this case actually are 12 bytes. So after this call, this is where the buffer overflow could happen. Whatever your input will be loaded to this place. And you can overflow starting from here to everything move to higher address. Then at the end of the instruction, this is also new instruction compared to the regular one. We first restore what EBP minus 4 is. We restore this to ECX. Then there is a leave instruction. Leave basically 2 instructions. Move ESP to EBP, then pop EBP. After that, we will move ESP to where ECX points to. Then we have the return instruction. So when you look at this, you find out that even though the beginning of this function tries to set up a larger return address copy on the stack, this part is never used, okay? If you look at this one is never used. Still, the old return address is used. This is what the return address used. However, if you override from here to here, you need to override everything in between. And the most important thing here is the saved ECX here. If you override this saved ECX, it will point to some other address. And we actually use that saved ECX, the saved EX, to find where is the return address. Okay. So one way to do this is to develop exploit somehow like this. There are 12 bytes of a buffer. Doesn't really matter what you put there, garbage. Then there's a saved ECX. You probably want to keep this ECX, those values intact. Okay, that's actually the hard part. Because you need to figure out what is saved here. You can debug to find out, but if you debug, the value you find out will be different from the value you just simply run the program. So I don't know how you guys find that. You did some calculation there, or just try? Yes, that's actually a very good strategy. A lot of, like I said, a lot of hacking require you to guess, and you can say security here relies on probability, right? As long as the entropy here is small, eventually you can the exploit will work. Actually, 2 weeks later, there's an attack we are going to do, and that requires us to do some guessing there. That one requires us to do guessing. There's no other way around. Then the saved EBP doesn't, I think this one you don't need to keep. Then this return address, since the code doesn't use this, doesn't really matter. Here, you also need to figure out the size of this. The return address here, you put the print secret address. Then this 4 bytes of garbage here, then you just put 3 arguments. So that is how you craft this exploit. But even if you have this picture, I guess it will take you, even now I explain to you how it works, I guess even from here, it may take you another hour to really find out what ECX works. Okay, that's my estimation. Yeah, maybe 1 hour. That's basically the 32-bit difficult version, and the 64-bit. The 64-bit version you can return to anywhere. Actually, you cannot return to the beginning of print secret. The reason is in 64-bit version. So many of you tried, right? Then you realize, oh, this is not working, right? Because if you return to the beginning of print secret, the program here will still try to compare those 3 arguments. But you find out you have no way to set those arguments because those arguments are in registers. They are not on stack. The attack you are doing here is a memory corruption attack. It's corrupting memory, okay? It's not corrupting register. It's not directly setting register, right? That's why I allow you to jump to anywhere. For example, if you jump to print flag, then you don't need to set a register. That function doesn't take any parameters. So in the second half of the class, we will learn a new approach that enable you to jump to the beginning of this function, but still you will be able to print the flag. So basically, you will know a technique called the return-oriented programming that will allow you to set up the registers. Okay, so that will be we will discuss in the second half of the class. Okay, so today we will move forward. We will talk about something we call frame pointer attack. Basically, we do not overwrite the return address of the current function on stack directly. We overwrite the saved EBP or RBP address, which we have been ignoring them so far. We overwrite them, and basically by doing this, we are changing the upper level function's return address. So this is our vulnerable program, overflow 6, level 6, 32-bit. The program is similar to what we had before. The main function takes 2 arguments, then it calls valfoo, and the valfoo takes whatever we input there. Then valfoo has a small buffer, C code level, only 4 bytes, and it will print out where the buffer is. This is just to make this easier for you guys. Then there is a string copy. No, sorry, not string copy, memory copy. Copy from your input to the buffer. Then we are copying 12 bytes. Those are carefully designed, so later you will say why I designed the 12 bytes there. There is no print flag in the address space, which means we have to inject the share-code in this case. For what we learned so far, we have to inject the share-code there. So with what we will learn later, return-oriented programming, you don't need to inject the share-code. So let's take a look at the disassembly here, line by line, not only the valfoo, but also the main function, and try to say, even if we cannot override the return address, how can we perform a control flow hijacking attack here? So let's say at the end of the valfoo function, the valfoo, you already know that, valfoo calls the memory copy, right? So which means you will be able to copy from the beginning of a buffer, then 12 bytes of it. And if you look at the disassembly, you can say, here is a memory copy. The first argument of memory copy is a destination, which is in register EAX. And the EAX actually points to EBP minus 8. Okay? So the EBP should be here, points to save the EBP. EBP minus 8 will be the beginning of this buffer, which means the memory copy will copy 12 bytes, right? Here, 0C, that's 12 in decimal, which means you can override the buffer 8 bytes, then you can override 4 bytes of the saved EBP. That's it, okay? No matter more bytes you are giving, you will not be able to override return or anything beyond that, okay? So this is different from all our previous vulnerable functions. Previous ones, you can override the return. Now you cannot do that. Then let's try to understand what happens here. Let's say we give 12 bytes of garbage there, 12 bytes of character A. Character A is probably 61 in decimal, or in hex, maybe. Anyway, we just put a letter A here. Assume those are letter A's. Here we have 8 bytes of A's. Then we EBP have 4 bytes of A's. Then when we execute the return instruction, what happens? Whatever ESP points to will be moved to the EIP, right? So ESP, before the return instruction, ESP actually points to return. That one is not changed. So after that, EIP will be set to the correct address, which is somewhere in the main function. However, before that, the leave instruction will pop the saved EBP. So this 4 A's those 4 characters will enter the register EBP. So you may question what is the meaning, the semantics of this saved EBP anyway. That basically points to the upper functions stack frame. There are so many functions, one calls another, and when one function have its own stack frame, it needs to reserve the previous upper level functions stack frame. That's why we save this EBP. Okay. So now we go to the main function. We just called valfoo. So this is the instruction to call valfoo. After we call valfoo, remember ESP points to here. Now we add ESP plus 4. So ESP moves up. So actually 4 bytes higher than the return address. We have the first argument for valfoo, which is the pointer P. Now we add ESP 4 bytes. So ESP points to 4 bytes higher than the first argument of valfoo here. We didn't touch EBP. We didn't touch the stack. So they stay the same. Right? EBP right now is still 4/8. Now we move 0 to EAX. The reason we do that is the main function is going to return. And the main function is going to return 0. We put the return address in the register EAX. Then after that, the main function will also do a leave. And the leave is equivalent to 2 instructions. The first one is move EBP to ESP. The next one is pop EBP. So let's see how that works. So when we do this leave, before that, our EBP has a value 4/8. So after this instruction, which means now both EBP and ESP has a value 4/8, right? Then we pop EBP. Pop is going to pop whatever ESP points to EBP, then increments the register ESP, which means we are going to dereference the address for character A's, which should be 41 in hex. We will dereference this address. So this could be a segment fault, because that address, we may not have anything. That may not be a mapped address. We are trying to read from an address that doesn't exist. We dereference that address, and the ESP will plus 4. So after this, ESP will have the value triple AE, because previously it's 4/8, right? Then after that, we are going to execute a return. And this return will be from that whatever ESP points to. So now we are going to return to whatever at the memory address triple AE there. Okay, that is how it works. Does that make sense? So that's why at least we have 2 memory dereference here and 2 chances to have a segment fault. Okay. So if we want to hack this program, any ideas? We want to take full control of this program. How do we do this? First of all, we want to put our share code in the address space, right? And that part is easy. We can just use environment variable. We put our share code in environment variable. Then we can get the address of our share code. Then we want to overwrite this address, save the EBP, and make it to point to our fake stack frame, and use the return address in the faked stack frame to return to our share code. Okay. So I'm going to show you at least 2 approaches here. Actually, there are many approaches. We're going to look at 2 approaches, and let's say one approach is this one. We can overwrite from this place to this place, 12 bytes. We can only overwrite 12 bytes, right? So we find out where this buffer is, where our input is, basically. And we call that address X. Then for those 12 bytes, the first 4 bytes, just garbage. We don't care about that. The second 4 bytes will be the address of our share-code, which we already inject there using environment variable. Then after that, the saved EBP, we are going to use the beginning of the buffer. Okay. So how this works? So when the main function returns, the main function will not think its own saved EBP or its EBP points to somewhere here. It's supposed to be somewhere here. It will not think that way. It will think its EBP will point to here. And the EBP will point to what? To main function, EBP points to what? For any function, its EBP points to the saved EBP. For the main function, the same thing. The main function will think, I have a saved EBP at this address. And what is that saved EBP? That is basically the stack frame of whoever called the main function. Okay. Then 4 bytes higher than that, what do we have? We have the return address that the main function should return to. Should be in the middle of the libc start main. Okay. Then that's basically it, right? So in this attack, even though the stack we are overriding technically is a Volfu's stack, but we are not overwriting Volfu's return address. Instead, on the buffer of Volfu, we create a fake stack frame of the function that calls Volfu, in this case, which is main function. And in that stack frame, there is a return address the upper layer function maintain will return to. And that address will override to the share code. So the real stack frame from main function is still here. It is intact. No one touched that. But the main function is not using that anymore. So that's the first way we can attack this. The second way, the same. The only difference is we put we know the buffer's address. We put the buffer's address -4 to the saved EBP. So the main function will not think my stack frame is here. Instead, it will think my stack frame is here, 4 bytes lower. And at this place, what it points to main function, it points to its saved EBP. And the value doesn't matter. So, and we do not have the ability to override that. But the value doesn't matter. No one uses that. Then 4 bytes higher will have the return address. Now we have the ability to override that, so we put the share code address here. Then after that, then 4 bytes no one use. Then there will be 4 bytes of garbage there, right? So that's the second approach. So the third approach is basically we are. So the third approach, actually, we don't need this part. There should be 8 bytes of garbage. So the third approach is we just put a fake main stack frame somewhere else, like in environment variable. As long as we know where it is and we can decide what we put there, then we can change this part, the saved EBP, to point to our fake main stack frame. Okay. So let's say a demo of this. This is overflow 6. So let's first, for any program you have, the first thing you want to try is you just run this program. So you already know that this program will only copy 12 bytes, right? So when I do this, what will happen? Will just exit silently, or it will have a segment fault? It will have a segment fault, right? So even if I do this, it means I will put so those parts I don't care, but I will put garbage in saved EBP. And the saved EBP will use as a main function's stack frame. So eventually, it will trigger a segment fault. So if I do this, it print out the buffer is at this place, and there is a segment fault. So let's debug this program and use 4A's, the same example I'm using there. So let's do at least 12 A's. Well, we can do more, it doesn't matter. Oh, I should set a breakpoint first. So let's set a breakpoint at the main function. Then we do 4A's. Okay. Now we add the beginning of the main function. Then we want to call valfoo. We want to go to valfoo. So now we are about to call valfoo. We use SI, step instruction to enter valfoo. If I use NI, it will go to this add instruction. If we use SI, it will step into valfoo. Now we are in the beginning of valfoo, as you can see. Now let's go to after the memory copy. Maybe here, let's say. Oh, we're using AT&T syntax here. I hope you don't mind. So let's do after memory copy. So now we are just returned from memory copy. So the stack has been overwritten, but only overwritten 12 bytes, right? So if we examine 12 words, just several, maybe 4 words from EBP. Let's say if we're from EBP, EBP will be here. Then we will say 4A's there. Then the return address there will be the right one, intact. So if we examine this way, oops, should use X. As you can see, that's a 4A's we have, right? That's the saved EBP. But the return address is the correct one, 5655. That's somewhere of the somewhere in the main function. Yeah. So you can say this is where's the main function? This is the main function. It will be this address, right? It will be 625D. As you can see here, 625D. That's a return address in the main function. Then higher than that, there is a parameter. That's why the parameters points to our input, which is a string on the stack. That's why it has a very high address. Then beyond that, we don't know what that is. So this is actually overwritten. So if we keep going, when we do a NI here, when we returns to 30, sorry. So now we are at 30. Now we're at 30. We're about to return. So return instruction will return to whatever ESP points to, right? And the ESP at this point points to the return address, which is 625D. That's correct. However, EBP already have the wrong value now. Info registers. You can say EBP, not EBX, EBP. EBP has 414141, those 4 A's. And that is because of that leave instruction. That leave instruction pops that 4 A's on the stack to EBP. And because of that, if we, where are we? We're at the end of val foo. Then when we run one more instruction, we are back at the main function. Okay. However, the EBP is wrong. Before that, if we do not have this, the EBP should be restored from the stack. However, at this point, EBP has the wrong value, which is 41, 41, 41. Okay. So then what we're going to do is there is another leave, and that leave may trigger the buffer, they trigger the segment fault. So this add will not trigger anything wrong, and this move 0 to EAX will not trigger anything wrong. Now we're going to the leave instruction. So look, we are at the leave instruction. And this leave instruction will move EBP to ESP, and we already know that EBP has 4 A's. So ESP, EBP, both of them will be 4 A's. Then it will do a pop EBP, which means it will dereference the memory address 41, 41, 41. And that may not be a valid address. Let's say if it is a valid address. So in GDB, we can examine that address. We just examine whatever is there. So when we examine that address at GDB, GDB tells us we cannot access memory at that address. Well, probably that address is not mapped. Okay, there's nothing in that address. That's why when we do this, this instruction is going to dereference that address, and it should trigger a segment fault. Okay, because that memory doesn't exist. So that's basically how why eventually that triggers segment fault. Then go back to how we try to exploit this. Did this program print out the? You should print out the buffers at some point. At the very beginning, I guess. I do not see when it was printed out. Okay, so when we run this program, you can say it print out where the buffer is. So if we use our first approach to the first exploit, then the X is that buffer's address, and we are going to put that address at the saved EBP. Then we put 4 bytes of garbage and the address of a share code. Let's put the share code in the address space first. So that's our share code. How do I copy this? So let's try to have a huge knob sled here. Okay, so now we have our long share code in the environment variable. We try to get a rough address of it. It's at this address. We have a huge knob sled, so we can add some number on top of this to try to jump to the middle of the knob sled. So our exploit will look like something like Python 2. it's on the stack, right? Stack is dynamic. So what determines the address of buffer? It depends on whatever was pushed onto stack first. And the command line arguments here, where are they? They're actually also on stack, right? So when I run this program using this command line argument, the buffer is at this address. Now my input is much bigger, right? The command line arguments is much longer. This is 1,000 bytes, 1,020 or 30 bytes. Here is just maybe 30 bytes. So actually the buffer's address will get much lower, right? So without running that, we don't know. So that's why when we use this address, it may not work, right? It doesn't work. But you see, the buffer's address changed. The buffer's address changed. But now you have your, now you have this part fixed. Now you have this part, oh, okay, sorry. It's not 1,000 bytes. It's just this number would be 12 bytes. But here is obviously not 12. So you can say they're still quite different. But those are also on stack now. Previously, they were not on stack. Okay, they're at the very top of the stack. So now, as long as you do not change this part, as long as you do not change the size of this part, okay, this number should not change anymore. So you just need to fix this address again. So now it should be 44 D2. Okay, this, let's say, this may work. D244 FF. It's not working. So it's probably this one, the share code. So where's the space? Oh, for the share code. Oh, I see. So the share code, there is a space. Okay. That may be the reason. So let's run this program again. The address, okay. Looks like at least we hit some instructions, but some of them are illegal. Then could be this one, we change a little bit. 54, D2. No, yeah, see? So that's how it works. So now we jump to the LOPSnet and eventually give us the share code. Okay, so that's the first approach, right? We put the buffer's address at the saved EBP. We have the address of share code. We have 4 bytes of garbage. So we can change this slightly. The saved EBP, we use the buffer's address -4, then share code the address at the very beginning, then 4 bytes of garbage after that. So we can just change this a little bit. So the buffer is at D2 54. So now we change to 50, right? -4 bytes. Then the share code should be at the beginning. The share code's address should be at the beginning of the buffer now. Then after that, we have 4 bytes of garbage. Okay, like this. Make sense? Yeah. It also gave us the flag. So if we are 1 byte off, let's say, instead of this, instead of 4 bytes of garbage, we put 5 bytes of garbage there, then obviously it will trigger a segment fault, right? That's how it works. Make sense? So the idea of this is to create a fake stack frame for the main function. We are utilizing the buffer to create that fake stack frame. We obviously can use other places. We can use environment variable, but the problem is we need to guess where it is. That will take longer time. You can write a script to do that. Here, to make it easier for you, I simply print out the buffer's address here. Okay. So now let's think, like I said last week, I always do this kind of practice. For any attack, we try to list the conditions that we depend on to pull off this attack. And if we take out one of those conditions, we make that attack harder to perform. Not necessarily we can stop the attack, but make it harder. The attackers can bypass this. But this is just another layer of defense. And attack and defense, they are always arms race between attackers and defenders. Attackers, they come up with a very smart approach, buffer overflow. Then defenders try to deploy all kinds of features in OS and also in CPU. Then defenders feel I'm safe. The attacker find out a totally new approach that bypass the existing defense. And we have seen this kind of arms race in the last several decades. And in this class, we also work through those kind of the history of that. So at this point, if we look at the conditions we depend on, I would say there are several conditions. The first one is the ability to put the share code on stack. This seems easy. We can put environment variables, command line, we can put it in buffer. Okay. Then the stack should also be executable. We are putting share code on stack. That's code. That's instructions. So the stack, that area must be executable. But if you are a developer, you are an OS developer, you think about this, it doesn't make sense. Whatever we put on stack, this should not be code. Code should go to the .text section, right? Whatever on stack should be just data. We should not make the stack executable. Also, we need the ability to override the return address on stack before one return instruction is executed, or from what we learned today, we should have the ability to override the saved EBP or RBP. Also, we need to know the address of the share code. That is where we want to return to. But with a very long snopsnet, we do not have to know the exact address of our share code. Make the bar for attacking a little bit lower. Okay. So the very first defense technique we will talk about is to take out the condition that the stack is executable. So this is a defense that have been deployed on all of our devices. We simply make the stack not executable. And this technique has many different names. If you read papers, if you read the CPU document, you may encounter several different names. Usually, I just call them data execution prevention. There are other names like write exclusive or X, or just an X, not executable. So the write and exclusive or X, it's also easy to understand. As long as this memory region is writable, then we cannot make this memory region executable as well. As long as the memory region is writable, what does that mean? It means attackers, anyone, can put things in this memory region. Then whatever they put there, we should not trust it. We should not think it's code. This could be a problem because some programs, they are called self-modifying programs, right? It means they can generate instructions at runtime. And there are many legit reasons to do that. Just-in-time compilers, JIT, just-in-time compilers, they are going to write something in the memory. They compile something at runtime. Just-in-time means right before we execute these instructions, those were actually just compiled. So there are legit reasons to do that as well. However, usually we don't believe there are legit reasons to make the stack executable. So there's actually some history behind this. Most of the systems we are using today, the hardware-wise, we are using the von Neumann architecture, which means we use the same memory bus to store data and to store instructions. So the bus is shared between data and instruction. Most of our computers we are using today are this way. There is another architecture. It's called a Harvard architecture, designed obviously by Harvard. So that architecture, they store machine instructions and data in separate memory units. So from one bus, you always get instructions. From another bus, you always get data. So you will never misinterpret data as instructions, right? I know some no-end IoT or embedded CPUs, they are in Harvard architecture, but most of our system right now, they are in this von Neumann architecture. Okay. So what we're discussing here applies to von Neumann architecture. So older CPUs, they don't have this DEP feature. They do not have the execution permission. Read implies execution. If the program can read a memory region, it implies that the program can also execute that region. Then, almost 20 years ago, AMD first introduced the NX bit, the not executable bit, which means a memory region can be readable, can be writable, and also we can say it's not executable. And 1 year later, Windows actually started to supporting this feature because the CPU offers this bit, but the OS may not be using that, right? So Windows XP started using this 2004. Linux also started supporting this in 2004. That's almost 20 years ago. So now we have many new permission bits. We have execution-only bit. So some memory region is not readable, it's not writable, it's only executable. Also, we have bits to say that this memory region is readable from the kernel only, or readable from the user net only, but kernel cannot read that. So we have many new features in the last 2 decades. And in MineApp, what we are doing is we think about those new features offered by CPUs, and we think about how we can utilize those features to secure the OS and applications. So since the OS supports that, the hardware supports that, compiler also need to support that. So GCC offers this parameter. So right now, the GCC, actually the default options will enable this DEP feature. So when you compile a program with GCC without giving any options, the stack will not be executable. If you want to disable this, you have to give this -z exec stack this option. So far, all the programs you have been hacking, we used this option to disable this protection. Okay. So this is a screenshot from the same program. One is OF, so basically the program you just saw, the overflow level 6. One is the regular version, which has the DEP. Another one is the regular one should be the one with DEP. The one you have been looking at is the one without DEP. And you can see here the difference. Even if we do not run this program, we just look at the L file, you can see this version, it says the stack. This is the stack. The stack is readable, writable, and executable with E here, right? So here, the same thing. Here is different. It's only readable and writable, okay? But this is just the compiled program. This is static, right? When the OS actually knows the program, the OS will read the metadata here and decide what to do, right? If the program said the stack should not be executable, the OS needs to honor that. We actually find out that many developers and researchers do not really understand how this works. They actually believe if you compile the program with this DEP, the program is automatically protected. It's not this case because this is actually enforced by the OS, not the program. Right? The program just tells the OS, I want the stack to be not executable. You should honor that, but there's no way to force the OS to do that. We actually find out in very low-end systems, the embedded systems, many, in one of the competitions we do every year, embedded CTF, we can see the code developed by any other teams. In that CTF, there are usually 20 teams, and each team will design a secure embedded system, then give their design source code to other teams to hack. We find out that last year, many teams, they used the flag of DEP. So basically, their flag tells when you compile this program, the stack should not be executable. However, we are developing an embedded system. There is no operating system. Okay? It's a bare metal system. So there was no one to honor that flag. Okay? Even though when you compile that, you are telling the stack should not be executable, but the OS layer, the noders, no one honors that. So the stack was still executable. So also, what DEP cannot prevent, it doesn't really prevent the corruption of the stack. It doesn't prevent the corruption of any data on stack. The return address, the function pointers, critical data, local variables, they do not protect that. So as long as the return address points to legit code sections, this cannot block any kind of control transfer. So next, we are going to look at how do we bypass this approach. Actually, you already learned how to bypass that. I just never tell you that you already know this. So this is attack called return to libc attack, and this can bypass that executable stack. So this approach was discovered by someone whose pseudonym is Solo Designers 27, 26 years ago. The approach I'm going to show you today, it will not return you a privileged shell, but you can imagine years ago it can. Okay, so the idea is very simple. We do not inject a shellcode into the address space. We do not put the shellcode in on the stack, because the stack is not executable anyway. You put a shellcode on stack, it's not going to work. Instead, we directly return to existing functions in the address space. So before this class, you have been returning to print flag function, right? But that function was created by me. Normal programs out there, they don't have that function in its address space. However, there are other very powerful functions in the program's address space. For example, the libc has one function called system. That function takes one argument, which is a command. You can treat that like a shell. So if you return to libc and give it a string like bin sh, it's supposed to create a shell for you. So this is the same as we return to any other functions, but you are returning to a libc function. So this is called a return to libc attack. So let's take a look at our next example. This is overflow return 4. The same overflow return 4 we looked at weeks ago. The main function takes, it doesn't look for command line arguments. This one takes input from stdin. There is a buffer, 30 bytes. And there is a gets function which can override the buffer. The only difference between this one and the one you looked at 2 weeks ago is when we compile this one, we said the stack should not be executable. So if you inject the shellcode there, you return to the shellcode, you will not be able to get the flag. However, let's say how we can use return to libc approach to hack this one. We go to challenge overflow 4, 32-bit, right? So we can, let's try to put the share code approach, right? And say why it doesn't work. We used the same approach before. Do I still have that share code? Okay, good. I still have the share code here. Let's put the share code. Oops. What's wrong? Okay. Let's put a large lopsided here. Oops, too big. Okay, that's our share code. Then that's the address of our share code. Then let's do obj dump. So we're looking at a vol foo, and you can say the buffer at EBP minus 30, which means if we want to hack this one, so 30 in hex, 48 plus 4, so we need 52 bytes of garbage. Then we need the address of our share code. We put something like, what do I have? Oops, don't have that anymore. I need to run that again. Okay, that's our share code address. So let's do that again. DA, let's do DB, 33, FF, right? That should be our, oops. That should be our exploit. So if we pipe this into the program, it should go to our share code, but in this case, I think the best way probably would debug this, right? So debug this, then you can say it actually jumps to the share code. However, it will not be able to execute that. So let's do GDB. To debug this program, we set maybe at a vol foo, breakpoint on vol foo. So we run this. So now we feed it to at standard input. So we need the 3, this one, then we put. So that's basically the syntax of this. You put 3 there. Then okay, let's see. Now we are at the beginning of vol foo, so we want to. We just set a breakpoint here. Continue. Now we are at the end of vol foo. So now we returns. We should return to our share code. Let's see if we return to our share code. We are returning to dbcc there. Let's see if that is our share code. Just 30 instructions at where the IP is. Oh, see, that is actually our share code, right? That's on stack. That's the middle of an object. That is our share code. Then we're at the, we cannot exam here. Let's just maybe do 5 instructions, whatever. Okay, so we're at the beginning of here. We're about to execute this NOP instruction. So we use SI to execute this. As you can see, we're trying to execute that, but we get a segment fault because that memory region is not executable. So when we try to execute that, the OS kills this process. That's why we cannot use this approach. I always get confused. You should exit or quit. Okay. So this approach doesn't work. That's why we want to use the return to libc approach. In the return to libc approach, we just return to libc function. Not only we only return to libc function, we are going to find the string /bin sh. We will find that string directly in this binary because the binary or the C library has that string already. Okay, we don't even need to inject that. So let's debug this program again. We debug this. We set a breakpoint at main. Then we run this program. And if you want to find out, so now all the libraries are loaded. We want to find out where they are. We just print system. And tells us the libc function system is at this address, F7 something. This is a region that is memory mapped to here. Many different processes, they probably share this C library because no one is going to change this, right? So now we want to, now we have this address. Then let's say, if we want to return there, then it would be easy. We do Python 2. How many bytes? 52? Yeah, 52 bytes. Then we just have that address, which is 3048 E1 F7, right? So if we, let me copy this one. If we rerun this program from this, did I set a breakpoint? Oh yeah, I set a breakpoint at the beginning of main. Let's just take a breakpoint at the beginning of system. I think we can do that directly, right? We set a breakpoint there. That looks like a different address. 48C0. Oh, that's the address. Okay. So if now we continue, if we successfully overflow, we should be able to trigger the breakpoint, right? So we could do this. So see, now we are in the program libc. So we successfully returned there, obviously, right? Because this is basically return to any function in the program. But at this point, we didn't set up the parameter. So if we continue running, it's not going to give us any shell. So the next step is we either put that string bin sh in the memory address space, or we just find one in the address space. Actually, I believe we can just find one. Let's say which command we should use to find one. I think there's a find command in GDB. Yeah, there's a find command. Find bin sh. So there is a syntax for that. I don't remember the syntax. Anyone here familiar with GDB? How do we find the memory regions file? Info files, right? I remember info files. Okay. So if you do info files, you can find the regions, and I think we're looking for libc regions. In libc, there probably will have a string like that. So let's say this one looks like no. This could be the libc, or it could be the loaders. Oh, here is libc. This is libc. Then we find the text in libc. Okay, here, this one. That's the region. So find, can we do a help here? What's the syntax? I remember probably just this. This is a region we're going to find, and Bing sh. We do not find that. Maybe we need to. Oh, we are looking at the text section. That's why. Let's just look at a bigger range. We should look at the data section. So here we have data. Here we have data. Yeah, this one looks like we may have something. Okay, let's use this region. Yeah, so the syntax is find, then the start address, the end address, and the string. Maybe they can do regular expression. You are trying to search there. Let's see. Even here we do not find something. Okay, let's do a bigger one, much bigger one. This is system, libc. Okay, from here is libc. Let's do this one. DC7BF. Okay, looks good. Okay, see? We find one. So actually, in this address space, there is already a string there. So we can examine that address. We just examine string, so which is S. We examine that address. Huh? What's going on? Oh, sorry. I should not dereference. Okay. See, at that address, so what I did is I put a star there. So when I put a star there, that's another layer of dereferencing. So we're actually using the string Bing sh as an address and find what is at an address. So you can say at this address F7 something, we have this string Bing sh, which means then we can reconstruct our exploit. So we have 52 bytes of garbage. We have the return address to system, right? Then we are going to put a parameter for the system, and the parameter is the address of that string. First, we need 4 bytes of garbage. 4 bytes of garbage here. Then we have the address of the string, which is 52, 13, F6, F7. Okay. So now we start from beginning. Let me copy this. So none of those addresses, they are actually on stack. They are not on stack, right? This one is the libc address, it's memory mapped. This one is also libc address memory mapped, which means even without using GDB, probably they will be the same address because they are not on stack. So we just continue around here. We continue around here. You see, it was actually successful. It created a child process. Okay, we're GDB it, that's why. Okay, which means the system, that say library function, create a share for us. So we just exit here every time. Okay, now we do this. We pipe into our program. It's, what's going on? Command not found. Okay, the $sign. Remove the $sign. Okay, let's say. So the address could be a little bit different. So here we get 61. What's the ASCII value for 61? That's lowercase a. That's lowercase a, and that's what we have there. We have this. Okay, any idea what's wrong here? Those addresses could be slightly different, but very unlikely. F7, F6, 1352. Okay, that looks correct. This one, F7, this one looks correct too. Yes, but those two addresses, they were not on stack. They were memory mapped. So very likely they are the same. Yeah. They are just C library addresses. Very likely they are the same. It's possible that they changed a little bit, but so let's see. No syntax error I find here. This part looks right. Well, when we do GDB, obviously it was successful. Oh, I forgot. If we want to get a share, we need to do a cat there, right? We need to do a cat. In the reading I gave you guys maybe 2 weeks ago, explained why do we need a cat. Let's see if this one works. Oh, it works. Okay, it actually works. However, it's not going to give us a privileged shell. That's because the system is the same as EXE7E. So we create a new process, then the shell we get only have the CTF. The user we have here is CTF. It's not root. So we don't have the share privilege. So we cannot really cat the flag here. Okay. But you can see that if you can return to other C library functions which do not create a new process, it will work, right? You just return to open. Then after open, you can return to, there are several parameters. It will be tricky to do that. But it's possible, right? Okay. So that's how return to libc works. Obviously, several years ago, it was working on our platform. But now with updated Ubuntu, it doesn't work anymore. You still get a share, but not a privileged one. Okay. So that's return to libc and how to bypass return to libc. In short, so far, all the attacks we are doing, we call them control flow hijacking attacks. The very first several examples we have, we were overwriting the local variables. We didn't hijack the control flow. Okay, but all other challenges we do so far, we overwrite the return address, we overwrite the saved EBP, eventually overwrite the return address. They are all control flow hijacking attacks. The goal is to hijack the control flow. And to hijack a control flow, the attacker needs to overwrite something called a code pointer. So here I'm borrowing the C concept of pointer. So in C programming language, what is a pointer? Right? So pointer is basically just an address. An address is a pointer, right? And a code pointer means that at that address, there are executable code, okay? So the return address on the stack, that's a code pointer. In C++, if you use classes in C++, at the beginning of the class, there are many virtual functions and virtual function addresses. And those are code pointers. They point to different functions. As long as you can override a code pointer and that code pointer is used, then you can hijack the control flow. So far, besides the return to libc attack, we are doing a very specific type of control flow attack. We call it code injection attack. We basically, it is a subclass of control flow hijacking, which subverts the intended control flow and to previously injected malicious code. And the requirement here is you need to inject your malicious code into the address space. And usually what we call the malicious code, we inject, we call them share code. The share code can be supplied by attackers. And it's just a machine code. It's raw bytes that can be CPU can interpret them as instructions directly. So the return to libc attack is actually a ladder type. In that return to libc, as you can see that we didn't inject any code, right? We only put two addresses there. One is a system functions address, another is a parameter bin /bin/sh's address. We didn't inject any code. We are reusing the code already in the address space. We didn't inject anything. So that's called the code reuse attack. Today we look at the return to libc. In the previous weeks, you return to print flag. So we are always reusing something already in the address space. What is more interesting is what we will study in the after we come back from midterm CTF. We will study return-oriented programming. So that one generalizes to all the gadgets in the address space, not necessarily reuse a full function like print flag or system, a function in the address space. We just find several pieces of instructions, several smaller sequence of instructions. Then we interleave those instructions together. We weave them together weave them together so they form a very powerful function we can use. And that is called return-oriented programming. And the center of that is still the return instruction. Also, we will study another variant of that, which is called jump-oriented instruction, which do not use the return instruction, you instead use a jump instruction. But we will talk about that later. Okay, so that's basically what I have for the lecturing part of this week. Next, we still have 1 hour, and I want you guys to start working on the homework. I already posted online, so I want to walk around to help you with the homework because I find out that many of you start very late with your homework and you come to my office hour right before the deadline and struggle there. And so I want to help you guys. So the homework today will be here. So this homework actually is due 2 weeks from now. And this class homework is quite easy. There is only a CrackMe version 5 that I didn't demo in the class. Everything else I demoed in class. But CrackMe 5 is something you need to figure out by yourself. So you can choose. Maybe you want to do CrackMe 5 first, so I can give you some hints, because there will be no videos of that. Okay, you can start now. I will be walking around.